Hi, in this video, I will explain fractal dimension and how to calculate it using geometry. So first, let's talk about regular dimensions. Let's take a one-dimensional object, a line segment. A line segment is one-dimensional because it only has a length, it doesn't have an area. And I ask this question, how many copies do I get if I magnify the length by 2? I have length in all caps because that's important. I will always magnify according to the length. Well, the answer is 2. Twice the length, 2 line segments. You can tell that if I multiply the length by 3, I get 3 copies. If I call the magnifying factor r and the number of copies n, then in one dimension, n equals r. Now 2 dimensions. Let's take a square. Same question. How many copies do I get if I magnify the length by 2? I magnify by a factor of r equals 2, I get a square with double the sides. How many of the whole square fit in it? 2 by 2 equals 4. I magnify by r equals 2, and I get n equals 4 copies. N equals 2 squared. Let's try a different number. What if I magnify by 3? Then I get 3 times 3 equals 9 copies. I see that the relation is that n equals to r squared. 3 dimensions now. I have a cube block. How many copies if I magnify the length by 2? I get a larger block where each side is multiplied by 2. It's a 2 by 2 by 2 block, so I have 8 copies in it. And I see that the relation is that n equals to r cubed. Let's try again with r equals 3. How many copies do I get if I magnify the length by 3? Then I have a huge block that's 3 by 3 by 3. Well, the top layer is 3 by 3, so that's 9 blocks. But I have 3 layers, so times 3 again equals 27. So yes, I just verified that n equals r to the third power. If I look back at the one-dimensional situation, I had n equals r. That can also be written as n equals r to the power 1. So let's look at it. If I define the letter d as the dimension, then when d equals to 1, n is equal to r to the power 1. When d is equal to 2, n is equal to r to power 2. And when d is equal to 3, n is equal to r to power 3. So the general rule is that if I have a figure in d dimensions and I magnify by a factor of r, then I would get r to the power d copies. The relationship is n equals r to the power d. So I'm ready to compute the formula for d. I can start with the relationship n equals r to the power d, and I isolate the variable d. For that, I need logarithms. So I go through some algebra, and I end up with d equals log of n divided by log of r. So that's the dimension formula. I define r and n according to what I've been doing. R is the magnifying factor. How much do I magnify by? And n is how many identical copies I get. Then d is equal to log of n divided by log of r. So I'm ready now to compute the dimension of a fractal figure. Let's take the Koch curve, also called the snowflake curve. The Koch curve starts with a line. I punch a hole in the middle 1/3 of it, and I put 2 sides of an equilateral triangle in its place. That gets me the first generation of the Koch curve. It has 4 line segments, so in each of those 4 line segments, I will do it again. I put a hole in the middle 1/3 of each line segment, and I put 2 sides of a triangle in it. And I do it again, and again, and again, and again, all the way to infinity. So the question is, what is the dimension of the Koch curve at infinity? So let's do the same thing as before. If I multiply the length by blank, I get blank copies. What should the first blank be? Well, since the snowflake curve is built by cutting out the middle 1/3, it's logical that I should use the number 3 for R. So I have a length that is 3 times the old length, and I magnify the Koch curve. How many copies of the original one are in the big magnified version? 4 copies. So my R is 3, my N is 4, and I plug it into the D formula, G equals log 4 divided by log 3. I get my calculator, and I get 1.262 approximately. So that means the Koch curve has dimension 1.262. It's a dimension with decimals. So when I first learned of fractal dimensions, I was excited that I'm no longer bound by the whole numbers. But I had a hard time imagining why it is that way. So here's how to think about fractal dimensions. A one-dimensional object is something that moves along in just one path. You may change directions, but you're still moving along just one path. It's nice, clean, crisp line with no thickness and covering no area. A two-dimensional object covers an area. It could be a circle, it could be a square, any figure, but it covers an area, and that's what makes it two-dimensional. Well, the Koch curve has a little bit of both. When we create the Koch curve, we create it by just drawing lines. We're not coloring in any area. But when we keep doing this and we get to infinity, then the final product doesn't look crisp and clean and doesn't look like someone just traveling along a path. It looks fuzzy. It looks like it may be covering some area. So it feels like it's something more than one dimension. But it's not quite 2 dimensions because we know it's not an area, it's just a bunch of lines, an infinite number of line segments. So that's the key, because of an infinite number of tiny lines make the fuzziness, and it makes the figure into something more than just 1 dimension, less than 2 dimensions, so it's 1 point something. All right, so let's do another example. This is the Sierpinski triangle. We started with the triangle. Euclidean is in 2 dimensions. Then we punch a hole in the middle of it. That gets us 3 little triangles, which we then punch a hole in the middle of them again. And then we repeat, and we repeat to infinity. If we keep going to infinity, then think about it like this. If there's any solid part left, we would be punching a hole in it. That means it feels like by the end, there will be just an infinite number of lines with no areas. So it seems like it's lost its second dimension. But to call it one-dimensional is also unfair, because in another way, no matter how much you punch a hole in a triangle, there will still be some triangles left. So there's always some vestiges of a second dimension in there. So we're going to compute the dimension. We know it's going to be lower than 2. It started with 2. It's not going to be 2 anymore. Same question. If I multiply the length by blank, I get blank copies. What should I multiply the length by? Well, lengthwise, I can see that the duplication goes by 2. I start with 1, it doubles to 2. I start with 2, it doubles to 4. So I should fill in the first blank with the number 2. Here's the larger magnified Sierpinski triangle after I multiplied the length by 2. Here's 1, 2, 3. So for R equals 2, I have N equals 3. I plug that in the formula for D, and I punch it in the calculator. I get 1.585. So the Sierpinski triangle has dimension 1.585. Summary. This is how you compute the fractal dimension. First, you look at the picture and you determine how it repeats. Does it repeat every time length multiplies by 2 or by 3 or by 4? Let that number be R. You multiply the length by that factor r, you magnify the figure according to that, and you see how many copies of the self-duplicating figure you get inside the new magnified figure. That would be your n. You compute d equals log n divided by log r. That's your dimension. All right, hope that helps. Thanks for watching. Bye.